Okay, so at the end of last time, I left you with a puzzle. So the puzzle is on the left screen. So it was a hunter who starts off at some place. Let's say this place over here, and he goes 1 mile south, 1 mile east, 1 mile north, and 1 mile west. And then it says he finds himself not in the place where he started, okay, which now we're looking at and saying, huh, wait, what? Then he shoots a bear. What color is the bear? Okay, so if we look on the Earth is a sphere, roughly speaking, a sphere, and there's a particular place called the North Pole, and that's where, and if you go on the surface of the sphere towards the North Pole, along a line of longitude, you will end up at the North Pole. So if we look at the North Pole from the top, so here is the North Pole, and if I start off here, let's say at the equator, and go north, then I'm going towards the North Pole. If I start over here at the equator and go north, I'm going in a different direction in real space, but as far as the geometry is concerned, I'm still going north. So let's suppose that we start off somewhere, let's say around here. So I'm going to go 1 mile south, and then 1 mile east, something like that, and then 1 mile north, something like this, and then 1 mile west, something like that. And so you can see that now I don't end up where I started. And the reason is that over here, this is a coordinate singularity. And that coordinate singularity is that when you're at the North Pole, all directions point south. Okay, if I'm here in San Diego and I just, say which way is south, I just look on my compass and I say it's that way, whatever it is. On the North Pole, every way is south. Okay, and so we have a coordinate singularity there, and so so the color of the bear is white because it's a polar bear, and polar bears live at the North Pole. Okay, so that's the answer to the riddle. Now, what the riddle is telling you then is that coordinate singularities have a strange and unfamiliar topology. So the take-home message is that coordinate singularities have an unusual consequence. And what I'm going to do today is I'm going to talk about coordinate singularities, but we're not going to be looking at the map and looking at north, south, east, west. We're going to be looking at coordinate singularities in the phase of the wave function of a condensate, such as a superfluid. So what we're going to do today is we're going to talk a little bit about whether or not there can be a phase transition in 2 dimensions in a superfluid, and we're going to see that there can be, and I'm going to show you a very simple argument for why that exists. Then I'm going to tell you a little bit about superfluidity, and I'm going to keep this introduction a very, very low level, okay? Because what I want to do is I want to, after today's lecture, next week, I want to start looking at pattern formation in non-equilibrium dynamical systems. So I'm not going to be going as deeply into superfluidity and Bose-Einstein condensates as I've done in previous classes. So we're just going to learn a little bit about to sort of wrap a bow around what we've been doing over the last couple of weeks in terms of the excitations and behavior of systems with continuous symmetries, and then we're going to go to a different topic. So what we're going to start off then with is the Kosterlitz-Thouless transition, and then we're going to be using sections of the notes that now come from my notes on emergent states of matter, as opposed to my notes from the renormalization group course. So when I say ESM, that means emergent states of matter, and those notes are on the Canva's website, and you can just download them. It's essentially an unpublished book with typos, so it needs to be corrected. And one day I will publish it as a regular book. Okay, so let's get started. And so I've drawn here, just because I'm going to need it later in the class, a coordinate singularity in an XY model. So let's just put that to one side for the moment, and let's look at a model of the XY model. So the next thing we're going to do is we're going to follow the section indicated there. So it'd be really great if people would come to class at the start and not come in 10 minutes late, please. Okay, because it's disruptive to the class when this happens, and you missed the introduction. So thank you. So we're going to write down the Hamiltonian for our system as the usual Hamiltonian. So I'll write it as J sum over INJ, SI dotted with SJ. And again, here we're going to have that the spins have a unit magnitude. So they have a unit magnitude and they also point in a particular direction. So if you think about a spin as if this is, say, the x-axis, here is the spin at that side I, so it's pointing with some angle theta, then this Hamiltonian I can write as J sum over I and J cosine of theta I minus theta j. So that's the difference between the angles. And if we assume that the spins are varying slowly over space, then I can think of this, I can do a Taylor expansion. So I can think of cosine theta as basically a constant as minus j over 2 theta I minus theta j squared plus higher order terms. And so basically what I can end up doing then is writing this essentially as some constant k, which is basically like j, but with some lattice spacing thrown in, and then integral d2r of grad theta squared. And so this is a long wavelength Hamiltonian for the 2D XY model. And theta here is the phase, okay? So that's the important thing. So in the next homework that you get, I think I had this as an optional question in the last homework, and it'll be a real question in the next one. Let me just walk you through a different perspective, so we can derive this in a different way. So, and that way is going to be one that starts with the Landau theory. And I want to show you this trick because it's it justifies something that I told you at the beginning of this section related to the freezing out of amplitude degrees of freedom. So I'm going to start off by writing down the Hamiltonian of the system as something like this. It's the integral d2r, and then I'm going to write it in this way. So grad psi squared plus u naught over 4 into mod psi squared minus r naught over u naught squared. Okay, so here now psi is, say, the wave function of a condensate, or it could be the O2 model order parameter. So it's a two-component order parameter, so it's a complex number. Something like that. Okay, now let's have a look at this. So this isn't the usual form of the Landau free energy. Landau free energy that we write down usually starts like this. It goes as grad psi squared, and then psi squared, and then psi to the fourth. But I've written it down in a very particular way here. So if you look at the term that's not the grad psi squared term, you can see it is psi squared minus r naught over u naught. So those are some numbers, all squared. So if I square that, it will have quartic terms, and it will have quadratic terms, and it will have constant terms. So this actually is another way of writing down a quartic Landau free energy, but this way is a particularly interesting way because when I take the limit as u goes to infinity, then you can see that the magnitude of psi is fixed. So let's write that down. So let's just say that this form of the effective Hamiltonian is equivalent to the usual psi squared plus psi fourth Landau free energy. As you can see by squaring the brackets. Okay. So what that means is I'm going to be interested in taking this limit. So if we look at the limit of u naught going to infinity. I don't literally mean infinity, but getting large, but at the same time, r naught over u naught equals fixed. So what that means is that I'm now looking at, since r naught is going to be large, that means I'm at temperatures much lower than Tc, and so now what's going to happen is the second term in the free energy is the most important one there, and so what's going to happen is the system is going to minimize that. So the minimum of the free energy is when psi squared equals absolute value of r naught over u naught, and so that means that the amplitude is fixed, but the phase can vary. So what that then means is that if I then work out what the grad psi squared term looks like, then the grad psi squared term ends up being basically grad theta squared. And so that's the second way that I can get this result. Okay, so now what I want to look at then is is a configuration of the phase. So that's drawn over here on the left hand side. So let's look over here, and let me make this red. In fact, let me make the pen just a little bit bigger. Okay, so you can see that the arrows go round this coordinate singularity. So there's a kind of coordinate singularity over there in the middle. Well, I can't define the phase. Okay, so over at this dot over here, the phase isn't well defined because there's nothing to point in that direction. But if I go to the neighboring lattice sites, then the spins have a well-defined phase and circle around like that. So what we're going to be thinking about is taking a contour around here. So I'm going to call that contour C. And we're going to ask what happens when I integrate that phase, the phase around this contour. So let's consider a configuration as shown on the left. So if we take the integral around this contour C of the integral d2r, no, actually not d2r, take that away, the line integral of grad theta plotted with dr. So what that is, that thing is equal to the integral d theta as I go around the curve, because grad theta dot dr is just d theta from multivariate calculus. And so, as you can see, as I go around this curve, theta goes round, changes by a factor of 2 pi. So in this configuration, it's equal to 2 pi. So you can imagine other configurations where as I go round the curve, the phase actually goes round by 4 pi or by 6 pi. So more generally, we can construct configurations where the line integral of grad theta dot dr is equal to n times 2 pi, where n can be -1. Well, n can be any integer, either positive or negative or 0. Okay. So those are configurations, and it has to be an integer because the phase can't have a discontinuity. So the phase, as I go around this curve, I have to get back to where I'm started, but the phase has to be continuous. So if the phase is going to be continuous, then I can't have a sudden jump in the phase. And so so that constraint then requires the phase to vary by a multiple of 2 pi. EJ, you had a question?
Yeah. So near the singularity, like that's the CR minus CR3 might not be a very small number.
Something fishy happens there. I'm about to explain what happens there. Okay. Yeah. You're totally right. There is something very funky that happens there. So let's go and see what that is. So so let's have a look then at what happens there. So let's suppose so clearly something funny happens near the origin. This configuration. So we want to write this thing down in a continuum limit. So what we're going to do is we're going to say, let's choose the radius r of our curve. So here is my curve. There is the radius r. So I'm going to choose that radius r to be much greater than the lattice spacing, so not in fact as shown in the picture there. And then the line integral around this curve sorry, there's a fire. Now the line integral around this curve is basically then going to be equal to the following. It's going to be 2 pi r times the magnitude of grad theta, and that has got to equal 2 pi n. And so then that what that tells you is that grad theta of r is proportional to n over r. So the grad theta, actually the gradient of theta actually scales as 1 over r. So why do we care about that? Well, then if I compute the energy of the system, the energy of this configuration, so this configuration, we're going to give it a name because it looks like a vortex. Things are sort of going around like this, so we're going to call this a vortex. So the energy of this configuration, we can simply write it down like this. It's 1/2 J times the integral over the volume of grad theta squared E2R, and the volume here is some system size L, so it's L squared, and because grad theta goes like 1 over R, then this integral is going to be logarithmically divergent. So I've got 1 over R squared coming from the grad theta, and then my D2R gives me an R dr d theta. So then I have an integral of 1 over R in the radial direction, and when I integrate that, I get a logarithmic divergence. So this is going to go like this. It's going to go like pi j, and then the logarithm of L over the lattice spacing A. And so that's going to be a logarithmically diverging. So this diverges as the system size goes to infinity. And what I've done is I've cut off the integral at the lower limit because the smallest limit is when the lattice spacing. I can't have any scales smaller than that, or I might be thinking of this as a coarse-grained free energy, in which case A could also be thought of as the inverse of the coarse graining scale in K-space. So that's the energy, and it diverges. So that says this configuration is extremely high energy. And why? Well, because as far out as I go, this configuration just keeps on going. And so I can't get rid of this configuration by making a local change. If I'm going to try to get rid of this configuration, every curve that I go around, so one thing I want to point out and stress is that as I go around this curve, notice here that the integral is equal to 2 pi. Okay, that integral doesn't depend on what is the radius of the curve. So there's the radius of my curve C. So we can say that notice that the line integral of grad theta dot dr is equal to 2 pi going around that contour C is independent of the radius of the contour. And so that means that it is, however big R is, I still get the same number. So if you say, can I get rid of this configuration, this high energy configuration, by making some small local change to spins? The answer is no, I can't. Because all the spins in the system, all the way out to L, they all give the same contribution to this line integral. So this means that this configuration has a topological charge. So small deformations of this configuration do not change this line integral. And this is one example of a topological defect. So why is it called a topological defect? Well, at the core, the order parameter actually it's in real life its magnitude goes to 0, so that means it's a defect, and it has a topological quantity that is conserved. It's called a topological defect. So we'll see a little bit more about that in a minute. And now I want to talk about what is the consequence of this. So what we've just learned so far, we have a very high energy configuration of a so-called vortex. And you might say, okay, so that's interesting, which has a topological charge. Okay, so what happens? So the question now is, what happens when we have two of them? So let's have a look at what happens when we have two of them. So let's draw our two vortices. So I'm going to draw them like this. So this is my attempt to draw this picture here. So I'm going to imagine drawing up those arrows. So those arrows create these configurations of the phase like this. And now I'm going to draw another one of those over here. What I should have done was just copy and paste it, shouldn't I? Okay, so here's another one. Something like that. So these. Actually, I don't want this one. I want a different vortex. So let me do that. I have a choice in which direction the vortices go. So I'm going to draw this vortex so it actually goes in this direction. Like so. So this vortex, this one has if I do the line integral, I get a plus 2 pi. This one, if I do the line integral, you can see it goes the opposite direction. I get minus 2 pi. Okay, so now let's take two of these things. And now I'm going to draw a contour that goes like this. Okay, so here is my contour C. So here's my contour, and I'm going to say let's have these things separated by a distance r, like that. So now I'm going to ask what happens if I go around this contour. So we know what happens if I go around the vortex on the left, I get plus 2 pi. If I go around the vortex on the right, I get minus 2 pi. And you'll probably see what happens when I go around both of them. So when I go around both of them, now there is no net topological charge enclosed by the contour. And why is that? Well, if you sort of look in the middle here, let me try not to destroy this picture. So here you've got a flow going like that, and well, here you've got a flow going like that as well. But if I go around the whole thing, then the flows cancel out. So the flow field far away from the vortices, cancels out, and so there's no net flow. So then what happens is, what is the energy of this configuration of two vortices? So this ends up being is the same form as before. It ends up, you can work it out, and I'll let you do that in homework. But it's still going to have the same form as before. You're still adding up the gradient theta squared of both of these configurations. So you're still going to get 1 over r's. You're still going to get logarithms. But what's going to happen now is the logarithm, whereas before the logarithm had as its scale the whole system size, now what happens is that the only relevant scale for that's in the system, on the scale of the system itself, you don't see any vortices at all. You only see the scale of the vortices on the scale of R. So what happens is the R gets replaced by, so the R replaces the L. So in this formula over here, so notice that here we have R, because this is the scale of the two vortices, and on the scale of L, there are no vortices. So we get the same formula as before, but L is now replaced by the separation between the vortices. And now that, when I take the system size limit, that does not diverge. Okay, so now what we're going to talk about is what happens at low temperatures. So Justin, you have a quick question?
Yes. None of this depends on the individual size of the vortices, right? Because
each vortex is infinitely big, right? But their flow configurations cancel out on scales which are large compared to the separation between them. So this is sort of like Gauss's law. Okay, Gauss's law is another example of this. In Gauss's law, you make your Gaussian surface, and that tells you how many charges are inside. It's the same kind of thing. Okay, so what I want to do now is I want to work out the free energy of vortices. Well, I'm going to make the claim that if I'm at low temperatures, so here is the idea. So at low temperatures, I'm going to claim that vortices get bound together in pairs. Which are equal and opposite. And then at high temperatures, then I'm going to claim that the vortices become unbound. That's what I'm working towards. Now, this clearly is not going to happen energetically, because energetically, if they're bound, and that's always going to, that's the, so far I've just calculated energy. So up to now, we just computed the energy, but if we're going to do thermodynamics, we need the free energy. So what we're going to do now is we're going to do the same argument that we did for 1 and 2 dimensions, where I showed you that there was order. This is now a couple of weeks ago. We did the Landau-Piles argument, where we saw that in 1 dimension, say for an Ising model, the entropy always destroys order. But in 2 dimensions, the entropy doesn't destroy order, and it gives you a finite transition temperature where the energy and the entropy balance. So now I'm going to do the same sort of argument, but now I'm going to be doing it with these topological defects. So let's we're going to ask ourselves what kind of temperatures do we need? So let's see why this could happen. So we know that the energy cost of a single vortex in a finite volume is E1. That's the thing that we already calculated on the previous page. So then the question is, what is the entropy? So to answer that, well, we say, well, how many lattice sites can the center of the vortex reside at? And well, the number of lattice sites, let's call them the number of lattice sites, well, that is L divided by the lattice spacing, or if you want the coarse graining volume, squared. So I could also write this as this. And so what that means is the entropy associated with the number of ways that I can put down a vortex is going to be KB times the logarithm of NL, which is going to be KB times the logarithm of L over lambda to the -1 squared. And that is just equal to 2KB logarithm of L over lambda to the -1. So now if I write down what is the free energy of an isolated vortex, so that is the free energy is equal to E1 minus T times S. So this is then just pi J minus 2 KBT times okay. So something weird happened there. I apologize for this. Zoom just decided to update itself in the middle of my class. What the heck? So what am I supposed to do now? Great. Okay, so I really apologize. I have to reboot. Okay, you're kidding me. Can somebody who's got a laptop open go to Teams and check that this thing is broadcasting, please? It looks like it reconnected and everything, but you never know. Okay, so let me finish this while Chan is checking for me. Okay, so let me just review because we got interrupted by Zoom crashing. So the energy has the form pi j times the logarithm of L over A, or L over L over the cutoff, and the entropy has a similar form. And so when I now put the two things together, then I just get the formula that I've written down there in the middle of the page. And so now what you can see then is that if I go to low temperature, the free energy of the system, let's call this free F1, goes to infinity as L goes to infinity. And at high temperature, F1 does not diverge. And the reason it does not diverge is because the entropy overcomes the energy of the single vortex. And so what I've just shown you is that is it working, Chan?
I'm not sharing the screen.
Thank you. All right. Thank you very much. Is the screen sharing now?
Yes. Works now.
Thank you very much. Okay, so so now we come back to where we were. So the free energy doesn't diverge at high temperatures, and so what that means is that what we've learned is that what is that low and what is high. So you can see that this transition occurs. There's a critical temperature. Tc is pi j over 2 kb, and so what we found is that for T greater than Tc, it is thermodynamically favorable to have single vortices floating around. And for temperatures less than Tc, it is not favorable. And the vortices will form bound states. And in a sense, you never see, at long distances, you never see isolated vortices. You just see the system and you don't see any topological things. So that is a topological phase transition. And we've computed this just by doing energy entropy type of arguments. Now, you might say, well, this is a bit of a fishy calculation, because really all I did was compute the energy of single vortices. And I showed you that two vortices together could form some kind of bound state where where if you look at them from a long distance away, you don't see the vortices at all. So you could say, well, maybe we ought to do this properly and consider the proper interactions between vortices. And that's exactly true. So what I can say is that this argument, so what we did was we neglected a proper accounting of vortex interactions. And then, of course, the other thing you have to worry about is how far apart all the different vortices are. They may form bound states on many different scales. So, in fact, the way you have to look at this problem is that the only way you can solve this properly is to do a renormalization group. So that was done by Kostelets and and Thouless, and so all of this was worked out properly. So we've neglected the proper counting of vortex interactions and the scale dependence. And that needs a renormalization group calculation, which tells you that in fact everything is okay, and the simple arguments I gave you indeed is giving you the correct answer. Okay, so that's the Kosterlitz-Thouless transition. So this is the first transition you've seen, which is topological. Now I want to go and talk about a different thing. What I want to talk about now is more less sensational consequences of ordering. So I want to talk about off-diagonal long-range order. And what I want to do is approach the topic of superfluidity. As I said, we're going to do this in a very simple and superficial way, which is by design. I want to just give you a flavor of it, but not go into too many details. Now, some of the calculation that I've shown you here about the Kosterlitz-Thouless transition, in the next homework, you will get an opportunity to do some of these calculations in a little bit more detail. And I'm not going to go through that in class. Okay, so let me find my place in the notes. And I want to skip ahead some of the quantum mechanical stuff. So this is what I want to talk about. Okay, so what we're going to do is, this is section in my class notes, 2.4.3. And what I want to show you is that off diagonal long range order gives you superfluidity. So I'm not going to go into a huge amount of detail about what off-diagonal long-range order is. What I think I'm going to do is I'm going to tell you in words what it is. I'm going to tell you at the end, if I have time, why we call it off-diagonal long-range order. I want to dwell on the consequences of it first, and then if I have time at the end, or maybe the beginning of the next lecture, then I'll go into a little bit more detail using a little bit of a second quantization. So let me just tell you what the basic idea is. And for the main thing I want to tell you about, you don't need any more than this basic idea. So the basic idea is, well, first of all, what is the question we're asking? And the question we're asking is, what are the physical consequences of having macroscopic occupation of a quantum state? So macroscopic occupation of a quantum state, a single quantum state, usually the ground state, has astounding properties. So first of all, let me just remind you what I mean by macroscopic occupation. What macroscopic occupation means is I have a fixed fraction of the particles in the system are in the same quantum state. And the important thing here is that it's a fixed fraction and not a fixed number. It has to be a fixed fraction so that as we take the thermodynamic limit, this effect doesn't go away. And usually when we're thinking about macroscopic occupation, we might be thinking of this as being the ground state And the interactions between the particles can push some of the particles into excited states. So if we wanted to delve deeply into superfluid statistical physics, we would then work out the occupation of the ground state. We would then calculate the excitation spectrum in detail, see what fraction of particles in the ground state, what in the excited states, and work that out in detail. So I'm not going to do that right now. What I am going to do is tell you what we mean by off-diagonal long-range order. So I'm going to skip the technical definition of it for Bose-Einstein condensates because I want to just give you the basic idea for now. So what I want to talk about then is we're going to say then that we have a macroscopic quantum state, which I'm going to call phi of r. So this macroscopic quantum state has a spatial dependence and obeys a Schrödinger type equation. So I'm going to say that this wave function has a form, some amplitude, which can vary in space, and then a phase that can vary in space. So I'll write it like that. And I'm going to say that the density of particles is going to go like phi squared. And so that's a squared. And I'm going to write this as rho s. I'm going to write it as the density of what's going to end up being the superfluid state. So we're going to call that the density. So then I'm going to write down the Schrödinger equation for this system. So the Schrödinger equation is just I h bar the wave function by dt is equal to minus h bar squared over 2m del squared phi plus whatever is the potential between them. And then if I want to work out what is the d by dt of the probability density phi squared. So that then is equal to minus 1 over 2m, the divergence of phi star, the momentum operator, and then phi plus the complex conjugate. And you should be able to derive that from basic quantum mechanics. And when I write down the momentum operator, what I mean is minus I h bar grad. So if you haven't seen that before, I'm not going to derive it now. If you haven't seen it before, ask me at office hours or message me in Teams. I can give you a resource you can look at in any elementary quantum mechanics book will tell you this. So what this means is that then if I write down what I have an equation of continuity, so that I can write this as Schrödinger equation for phi squared as the following: d by dt of rho s plus div j is equal to 0. So this is an equation for the conservation of probability, and my current that goes along with the density is then just 1 over 2m phi star p phi plus the complex conjugate. And now remember that our order parameter, our wave function rather, is phi is a e to the I gamma. And so if I plug that into this equation, and what I get is that the current J is equal to rho s over m h bar times grad of gamma. And so this is something that you should check. It's only a couple of lines of algebra, and now I want to consider the physical consequence of this. So when you're normally given an equation like this equation here is a continuity equation. Just like you have an electromagnet, you have a density, you have a bunch of particles moving with some velocity. And so when I write down d rho by dt is equal to this, then I can think of this J is equal to the density of whatever the stuff is times its velocity. And I'll call the velocity Vs because we're talking about a superfluid. So current is this is the conventional definition of current. And so what we've just learned from this by looking at these two equations, what we've actually learned is that the velocity of this superfluid current, whatever it is, of quantum particles in a condensate, is given by the gradient of the phase of the wave function, and it's multiplied by h bar over m. So we have in our system with a macroscopic occupied quantum state, it has a velocity field that flows, and the velocity field can flow and is driven associated to gradients in the phase of the wave function. Okay, so what is the physical significance of that? So you might say, well, this is just some math trick. You know, who cares? What does it mean? Well, this Vs, so rho s and Vs, they are the density and velocity of the atoms in the macroscopic occupied state of the system. Let's say the ground state. So that wave function describes those particles. There are also excited states and particles associated with those. And they're not described by this formula. So if I were to think of my physical system, it looks like this. Here's my box, my L by L box, and it has in it particles, which I'm drawing in yellow. And these particles that I'm drawing in yellow are the excited states. And they're excited states, they're particles, they have no funny quantum mechanical stuff. So those things behave just like a regular fluid. But also in the same place, in the same points in space, there's also the condensate, the macroscopically occupied quantum state. And these particles, and this behaves with a velocity field, Vs, which is given by the equation on the left. So if these particles here behave like a regular fluid, what that means is that they obey the Navier-Stokes equations. And that means that they have viscosity. And the macroscopically occupied states, they obey this funky equation over here on the left. And now I want to talk about what is the fluid mechanical behavior of these particles. So now the question is, the excited states they equal a Navier-Stokes fluid. So the question is, what is the behavior of the condensate? When I use the word condensate, I'm using it as an abbreviation for a Bose-Einstein condensate, which is a macroscopically occupied ground state of a system of bosons. So that would be the physical realization of this. So let's talk about what this thing looks like. So let me just get to the right point in my notes so I tell you the right thing. Okay, so here. So the next thing I want to tell you then is the following. So to answer this question, so what do we know about the superfluid? The superfluid component, as we'll call it, behaves like this. And notice that it has a gradient of a potential. So one of the things that you learned on your mother's knee is that if I take the curl of Vs, and that's the curl of grad is equal to 0, so the curl should be equal to 0. So this is a fluid that has is curl free. Okay, so who cares? Okay, so now we want to ask. Okay, why does this matter? This matters because of the way we measure viscosity. So let's think how we measure viscosity. So what you do is you take a fluid between two plates like this. So here are two plates, and then you shear the fluid. So this plate is moving in this direction. This plate is moving in this direction. And in the middle is the fluid. So let's ask ourselves, what does the velocity look like in the fluid? So I'm going to set up a coordinate system. So let's set up a coordinate system that looks like this. We'll call this direction X and this direction Z, and there's a Y direction perpendicular to my screen. And we're just going to assume that everything is the same in the Y direction. So the fluid has a zero slip boundary condition at the surface. So think about this. The surface is moving, but there's no slip at the surface. So that means that the atoms in the fluid that are in contact with the surface, they're being dragged along with the surface. So the ones at the top are being dragged along to the left, to the right. The ones at the bottom are being dragged along to the left. Then the ones in the middle inside the fluid, all they see, they don't see the surfaces at all. What they see are just the neighboring fluid particles. So we can imagine then what the velocity profile is going to look like. So the velocity over here at the top, that bit of fluid is going to be moving with the speed of the actual boundary itself. And then gradually over here, the atoms over here are going to be moving with this boundary. So what's going to happen in between? Well, you can fill in the gaps. You're going to get something that looks like this. I haven't drawn it very well, but something that's going to look like that. That's going to be the velocity of the system. Okay, so that's what it looks like. So I can write that down in the following way. I can say that the velocity field in this fluid is Vx it's going in the x direction, but it is a function of the height z above the lower plate, and then there's nothing in the y direction or the z direction. So this follows because of the no slip boundary condition at the walls. And why do we know it looks like this? Well, we know that there's a viscous drag. And that viscous drag is associated with the velocity gradient in the fluid. So what we have to do in order to, so if all the fluid is moving at the same speed, there's going to be no drag. If the fluid is moving differentially in space, then I have to apply a force to overcome the viscosity to make it do that. So basically, to move the plates, the boundaries in the way that I've described, we need to apply a force per unit area. So I have to apply a force per unit area. And how big a force? Well, if the velocity, here is the velocity gradient that you can see over here. And the bigger is that velocity gradient, the bigger force that I need to apply. So you would expect that to a first approximation, the velocity gradient, the force per unit area is going to be proportional to the velocity gradient. And that velocity gradient is dvx by dz. And there might be higher order terms, but at least in the approximation where the flow is laminar, as I've used here, then the lowest order term is the one that we're going to be interested in. And there's going to be a coefficient of proportionality here. And that coefficient we write down as eta, and this thing is called the shear viscosity. So that's what I measure when we try to measure the shear viscosity of a fluid. So we put the fluid in here, and then if it's really easy to shear it, then it has very little viscosity. If it's really thick, like honey or treacle or something like that, then it's really hard to do it. You have to apply a huge force in order to create a desired velocity gradient. So the question is, what force do I need to apply in order to get the velocity gradient that I want? And the answer is, it's proportional to that velocity gradient with a coefficient that is something to do with the nature of the fluid. If eta is big, you've got viscous honey. If eta is small, you've got maybe a gas or something like that. Okay, so now what do we know about our system? Well, our system obeys an equation of motion. That is what I wrote down over here. We saw that curl V is equal to 0 because the velocity is given by the gradient of the phase of a macroscopically occupied wave function. So now let's calculate what is the shear, what is the shear viscosity, what is the shear viscosity for the superfluid component of the system. So I know that the superfluid component has a velocity that obeys curl V is equal to 0. And that means that if I compute dvx by dz, minus dvz by dx. That's the first component. And then there's the y component, and then there's the z component. Okay, but these ones are both 0 because the velocity field is just 0 and 0. So the only term that we have to focus on is this term. But we know that v in the z direction is equal to 0. And we know that this curl is equal to 0. So we know that therefore dvx by dz is equal to 0. And so then that means that the force per unit area that I need in order to create the situation then is 0. So even though this shear viscosity might not be actually 0, the force per unit area is equal to 0. And so that's why we get a superfluid. So the superfluid seems to have no shear viscosity. And this is a consequence of the macroscopic occupation of the quantum state. So does this really apply to the real world? So yes, it does. So the answer is yes. The first example that was discovered was the phase of helium-4. So that for temperatures less than about 2.2 degrees Kelvin undergoes Bose-Einstein condensation and then becomes a superfluid. So this, what I've just explained to you, is actually observed in the real system. This is the actual explanation of that. Okay, so there's more I can tell you about this, but I think I'm going to stop there for now. I think we're not going to go too much into the details of quantum vortex lines. I think what I might do is just tell you a little bit. I think I've got 3 minutes left. So let me tell you just a little bit about persistent currents. So this will be the last topic, 2.4.4, persistent currents. And I may carry this on just a little bit next time. Okay, so what I want to show you is that superfluids are a perpetual motion machine. Okay, so that's what we're going to talk about, is perpetual motion. So let's now imagine we have a donut like this. Okay, so there's my donut, and the superfluid is occupying the middle region like this. And now what I'm going to do is I'm going to draw a contour that goes through the middle of this superfluid region. It's meant to go through the middle of it, but I can't draw it very well. So there's my contour, and we'll say that this contour is out at a radius, let's say r, from the center of this annulus. Now, what I want to show you, the goal of this little section is I'm going to show you that the single valuedness of the quantum wave function means that I can have persistent currents, which means perpetual motion. So the goal is to show you that this geometry exhibits a perpetual motion a current that you can measure that never decays. And never is a long term, but at least say within the lifetime of the universe or something like that. Okay, so how are we going to see that? So let's do it like this. I want you to imagine that I take, let me use a different color. I take three different points around this circuit. So I'm going to look at those points R1, R2, and R3. And what we're going to do, and we're going to finish this next time. What we're going to do is we're going to assume that the amplitude of the wave function is a constant, and ask the question, what happens to the phase? As we go around this circuit. So that's the question. And what we're going to see next time, there's just a couple of lines of algebra. What we're going to see next time is that actually this thing can have currents that go around and never decay. So I'm going to show you that, and that will be the last thing we'll talk about in superfluids, and then we'll go on start looking at pattern formation in biological and physical systems. Unless the class says no, we want to know more about superfluids and quantum mechanics. So if anybody has a desperate desire to do that, then let me know. But otherwise, I'd like to go on to another emergent topic. So we'll finish this off next time, and you have a homework that I sent out before. I've also asked you to give me your term papers, to your titles and abstracts. If you have any questions about that, you want some help, you want some suggestions, please don't hesitate to ask. The algorithm is you'll give me your titles and abstracts and some references that you plan to use. I will look that over and I'll say, yeah, this is great, but here's a couple of references that you might want to look at that might be interesting for your essay and your presentation, and that's how we'll do that. Okay, so that's the end for today. So thank you very much. And I'll put all this stuff on the website. All right, let's go back to Zoom. Let's stop the recording.